Good morning, one and all. Today we are going to discuss pushdown automata. As you know, finite state automata, finite state automata is used to accept regular sets, and likewise pushdown automaton or PDA is used for accepting context-free grammars. These grammars we'll discuss later. Anyway, there are some languages which can be accepted by finite state automata. Why? This finite state automata has limited power. That means it has finite amount of memory. But in this case, in the case of PDA, it has got more memory compared to the finite state automaton. That means infinitely large memory is there for PDA, but here in the case of finite state automaton, it is having limited amount of memory. That is why for certain languages we use PDA. For example, in our previous classes or in our discussions regarding finite state automaton, using pumping lemma, we proved that 0 raised to n, 1 raised to n, where n greater than or equal to 1 is not regular. That means a 0 power n, 1 power n. That means n number of zeros followed by n number of ones. That means initially you have to count or you have to remember how many zeros are there, and after that when you're processing one, you should remember this zero and the number of zeros and number of ones should be the same. So we are not able to design a finite state automaton for that. So we have another tool or another automaton which is used for accepting this type of languages, that is called pushdown automaton. And in a pushdown automaton we have in our finite, just like our finite automaton, which is a finite control. This is the finite control. And in our finite state automaton also we have a finite control. And here we have an input tape. This is the input tape. And here A1, A2, etc. up to AI, etc. up to AN. That means here we have an input tape and the input is printed on this tape, and initially the finite control is pointing to this first location. Initially the finite control is pointing to the first location. This is just like our finite automaton, but unlike finite automaton, it has another structure which is called as stack, and the bottom of the stack is represented by Z0, and here we have a number of elements, and Z is on top of the stack. Another name for this is pushdown store, or that is why we have pushdown automaton. That means this is stack means you are pushing elements onto the stack and popping from the same side. That means this is a LIFO structure. And we know all those things. That means here in the case of a pushdown automaton, it is the finite control is pointing to some element or some input symbol of the tape, and at the same time the finite control is looking onto the stack and on the top of the stack. Okay, that means the stack is used for memory. This is actually providing the memory for pushdown automaton. A pushdown automaton m is equal to, it can be a 7 tuple, q sigma gamma delta Q0, Z0, F. Here Q is a set of states. Sigma is Q, just like our finite automaton. This finite control will be in any one of the states. This finite control will be in any one of the states. And sigma is the input alphabet. That means the set of allowable symbols in the state. And this gamma is the stack alphabet. That means here this stack is having an alphabet, and only from that alphabet symbols can be pushed as well as popped. Okay. Then delta is the transition function that we will discuss, and Q0 is the start state. Q0 is the start state for this finite control. Z0 is the bottom of this stack, and F is the set of finite states. Compared to finite state automaton, here we have two more symbols. That means this is gamma and Z0. These two are regarding this stack, and Z0 is the bottom. It is the bottom of stack marker, and this is the stack alphabet. Or from this alphabet only we can push elements onto the stack. Now we are going to discuss how a pushdown automaton is working. That we are going to discuss. So here what we are going to do is, I am going to design a finite automaton which is accepting the language L is equal to WCW, where W is an element of sigma star. Okay, this is the language accepted. That means here W, here sigma is equal to 0, 1, and C is the middle. That means, for example, suppose that you have a string and you have another string, say 0, 0, 1. Then here also it is 0, 0, 1, and in between you have C. That means WCW. And suppose that I am going to have WCW raised to R. That means this string. That means here you have a string followed by C, and this string which is in reversed form. That means, for example, the language accepted by this is, for example, the language accepted is here 0, 0, 1. That means when this is W and when this is written in reversed form, you have 1, 0, 0. That can be accepted. That means a string followed by C followed by the string which is in reversed form. Okay. For example, suppose that you have 0, 0, 0, 1, 0. Then after that C. Now you have to start from here. That means 0, 1, 0, 0, 0. That means here we have a string. Here that string is W followed by C. C is a terminal. That means nothing can be derived from C. And W raised to R means this string which is in reversed form. Okay, that is the string that we are going to accept. Okay, string which is in reversed form. That means L is equal to WCW raised to R, where W is an element of sigma star. That means 0 or more symbols from 0, 1. That means the string contains, that means this W contains only zeros and ones. That is the meaning. And for accepting this, I am going to design a finite automaton, not a finite automaton, a pushdown automaton for accepting this. It is looking like this. Here you have a stack, or suppose that you have a stack of plates. This is a stack of plates. You have a stack of plates, and initially at the bottom of the stack you have a red plate. Here you have a red plate. At the bottom you have a red plate, and after that you have say 0, 0, 1, C, 1, 0, 0. What you are going to do is, here initially you are in state Q1. That means the finite control, suppose that this is the finite control and this is the finite control, and the state information is, that means this is in state q1. Initially that will be in state q1 and the input is written on this state, and initially the finite control is pointing to the first 0. Initially that is pointing to the first symbol of the string. And what will happen here? These are the set of these are the moves we are going to define. And in simple terms, what you are going to do is, if you have a red plate and in state q1 you are adding plates to this stack. Okay, that means if a 0 is coming, you have to add blue plate, and if a 1 is coming, you are going to add red plates until they are encounters a C. That means until the C, that means up to this point, this will be in state q1, and once this finite control reads this C, that is switching to state q2, and here for all these w raised to r, this will be in state q2, and upon that means after reading the last symbol of the string, if the stack is empty, that means that can be accepted. That means you keep on adding plates to this stack until there encounters a C. That means until that C, you keep on adding plates to this stack. That means this is a stack of plates. It is just like our stack in the finite control. And here, suppose that these are stack of plates. That means you are adding in just like your CD that CD stack. You know that. Likewise, here also we have a stack of plates, and the bottom of stack is you have a red plate. And suppose that initially this is the top plate, and I'll show you how this is going to happen or how this is done. Suppose that a 0 is coming, and suppose that the top of the plate is red, and now the state is q1. That means the finite control is in state q1 and the top of the plate is red. That means a red q1, and if the input symbol is 0, what will happen? Add a blue plate and stay in q1. That means this is not add blue state, actually add blue plate, and the next state is q1. That means here you are not going to change this q1, and here you have added a blue plate. This is blue plate you have added, and you are moving on to the next. That means finite control is now pointing to next 0. See, now the top of the plate is, now the top is pointing to a blue plate, and the next input is 0. What will happen? If the top of the plate is blue and the next input is 0 and the current state is q1, again you are adding blue plate and state in q1. That means again you are going to add a blue plate. This is blue, and you are advancing your input pointer to the next element. Okay, you are advancing your input to the next element. Now what is this one? What will happen? The current top is having blue. That means the current top is blue, and the current input is pointing to 1. That means blue plate, current state is q1 and 1. That means if you have a 0, you are going to add blue plate, and if it is a 1, you are going to add a green plate. That means you keep on adding blue plate if the finite control is reading a 0, and if it is reading a 1, it is adding a green plate. Okay, that means here now we are in state Q1, current top of the plate, current top is blue, and as it is a 1, the finite control is pointing to 1, you are going to add green plate. This is green. This is green. Okay, that means next is the symbol C. What will happen? If now the current top is having green and current state is Q1 and you are reading C, that means current top is having green and current input is C and current state is Q1, that means green Q1 and C, what will happen? Go to state Q2. That means you are not going to add anything. You have switched to state Q2 without adding any plates. That means now this has changed to Q2. Okay, this has changed to Q2. Now what will happen? The input pointer is advanced. Input pointer is advanced to the next input. That means now it is pointing to 1. That means if the current top is having green, that means this is the row corresponding to that. And if the current state is Q2, that means green and Q2. If there encounters a 1, that means green, Q2 and 1. That means here 0, 0, 1, C, 1, 0, 0. If this has to be a valid grammar, then this 1 has to come here. If it is 0, it is not a valid string. It is not a valid string. So it is expecting a 1. That is why here green Q2, and if there encounters a 0, that is an error. If there encounters a 1, that means now you are going to pop that plate. That means you are going to remove that plate. That means here, as this is a 1, you have added a green plate. And after this you are expecting a 1, and up to that point it is valid, so you are going to pop that 1. That means popping 1 means you are popping the green plate. You are popping the green plate. Okay, now you have popped the green plate, and now you are moving to the next one. That means 0. Again, what will happen? Now the current top is having blue, that means this row, and current state is Q2, that means in state Q1 you are adding plates and in state Q2 you are removing plates. That means W, that means for remembering this W only you are going to use this tab. Okay, that means if you have say 100 elements in W, 100 elements in W or 100 symbols in W, you have to add 100 plates, and after this you are expecting 100 plates which is in reverse direction. That means you are going to remove one by one. Okay, remove it one by one, and that means here in state Q2 you are checking whether that means it is expecting each element. That means next element expected is 0. Why? Here after this one there is a 0. So here you have 1, you have 1, and it is expecting a 0. If there encounters 0, 1, what will happen? Error. That means this is not defined and this and this are not defined means if there encounters such pairs or such such a transition, what will happen? Such a transition, that means it's an error. Okay, here now the top of the plate is having blue and your finite control is in state Q2, and the next element you are going to read is 0. That means blue, Q2 and 0. Remove blue plate. That means here we are going to remove blue plate. Okay, and now the top of the stack is pointing to blue, and again it is staying in state Q2, and now you are advancing to your input pointer to this. Okay, And now again blue Q2 and 0. Blue Q2 and 0 means you are removing that blue plate. That means here you are removing that blue plate. Removing the blue plate, and you are staying in the same state, and you are moving to the last element. That means now you have reached the end of the input. End of the input. That means all your input have been consumed. All the input have been consumed, and now you have this is top of the stack is having red. So top is having red, and if the finite control is in state Q2, that means once you reach this state, then red on Q2 means without waiting for input. Now means no more inputs are allowed. That means without waiting for input, remove red plate. That means here we are going to remove the red plate. That means now this is empty. Now this is empty means this is a valid string. This is a valid string. This is a valid string. Okay. That means this can be accepted. That means WCW. So in such a case, you can accept that string. WCW raised to R. Okay. Now, this is the way pushdown automata is working, and now I am going to have defined a finite pushdown automata for this. M is equal to, this is the PDA, M is equal to Q sigma gamma delta Q0 Z0 F. And now this is not having any final states. So here we have defined a finite automaton or pushdown automaton, not a finite automaton. We have defined a pushdown automaton, and there are two types of pushdown automaton. That means accepting by final state and accepting by empty stack. Now we have discussed a finite automaton which is accepting a language by emptying the stack. That means once you have processed all the input, after processing the input, if the stack is empty, that means it can be accepted. So that kind of a finite automaton is represented by 5. That means here there is no relevance for the final state. That means that is 5. Here we don't have any final state. That means this is accepting a language when after processing the input, if the stack is empty, that means that can be accepted. That can be accepted. Here, for example, here Q is the set Q1, Q2. Here you are having Q is equal to Q1, Q2. Now sigma is equal to 0, 1, C. That means the input is having 3 symbols. That means 0, 1 and small c. That means WC, W raised to R. This W and W raised to R should contain only zeros and ones. But apart from that, or in here also you are going to have 0, 1, C, and this is sigma minus C. That means star. That means this W should not contain any C. That is the meaning. So Q sigma and gamma is the stack alphabet. That means the set of stack symbols. That means here you have red plate, blue plate and green plate. That means there are 3 types of plates or 3 types of inputs elements in the stack. They are R, B and G. And this delta will define, and Q0 here is not Q0. Initially the finite control is in state Q1. So Q1 is the start state, And Z0, what is Z0? That means bottom of stack marker, and in this case we have used red as the bottom of the stack. Red is at the bottom of the stack, and this is accepting by emptying the stack. So sigma q1 red and this one. That means now I am going to define the transitions for this delta. That means delta of q1. That means delta of q1 0, and if you have a red plate, what will happen? That means if the current state is q1 and if the finite control is pointing to 0 and the current top of the stack is, that means initially here an instantaneous description of a finite control is having three elements. An ID of instantaneous description, instantaneous or ID, instantaneous description of a PDA. That means PDA is actually, it's a finite control. PDA is having three elements: finite control, stack and input. Okay. Once this instantaneous description means here you have three elements Q, A, Z. That means Q is current state of finite control, current state of finite control. Okay, what is A? This is input symbol, current input symbol. This is the current input symbol, and this one is current top of stack. That means here you have three elements for an instantaneous. At any point in time, the PDA or the finite control of the PDA is in some state, that is represented by Q1. It is pointing to some input symbol, and that is represented by A, and it is pointing to pointing to the top of the stack. That means top of the stack is pointed to by Z. At any point in time, you have an instantaneous description like this, and now I am going to define delta for this. That means this is simply given as this one, and now delta of Q1. That means if your finite control is in state Q1, and if it is reading an element 0, and if the current top of the stack is having red, what will happen? Q1 0R. What will happen? That means red is pointed to various Q1 and 0. What will happen? Add a blue plate and stay in state Q1. That means this is represented by Q1. It is staying in the same state after pushing a blue plate. That means you are pushing a blue plate means pushing that on the left hand side. That means BR. That means thus red is replaced with BR means above that red plate you are going to add a blue plate. That means Q1 BR. Now what about Q1 1R? That means if the current top is having red and the current state is Q1, and if you are adding 1, what will happen? Green plate is added. Green plate is added means this is Q1 followed by GR. Green plate is added. Green plate is added. Okay. Now these are the two moves for red, and now suppose that you are in state Q1, delta of Q1 0, and if you are having a blue plate on the top, blue plate Q1 and 0, again you are going to add a blue plate. That means this blue is replaced with blue. That means now the top of the stack is having blue, you are going to replace that with B and B. Okay. That is, again it is staying in the same state Q1 and you are adding BB. And suppose that in state Q1, there encounters a 1, and if the current top is having blue, what will happen? It is staying in the same state Q1 and a green plate is added, that is GB. Now, suppose that delta of Q1 0 and green. Suppose that Q1 0 and green. That means current top is having green, current state is Q1 and you are adding a 0. What will happen? A green, this is not green plate actually, this is blue plate. Okay, blue plate. And we are going to add, that means if there encounters 0, add blue plate, add blue plate, add blue plate. If it is 1, add green plate, add green plate, add green plate. Okay. And likewise, here 0G, what will happen? Here you are staying in the same state Q1 and this is replaced by GG. Now what will happen if delta of Q1 0B? What is Q1 0B? Q1 0B. That means this is not Q1 0B. That is Q1 1G. That means this is state Q1 and the next input is 1 and current of the stack is green. What will happen? This is staying in the same state Q1 and this is replaced by GG. Here actually it is blue green. As the 0 is coming, this green is replaced with blue green. And like this, we can, or rest of the transitions also I am going to write delta of Q1 C. And if the top is having blue, what will happen? That means Q2. That means here in state Q1, if it is accepting C and if the current top is having blue, then you are not going to do anything with the stack. You are just changing your state to Q2 and this B is replaced again with B. That means you are not going to do alter the state or not going to do anything. Now delta of Q1 C and suppose that green is on top, again Q2 green. Okay. Now what will happen if delta of Q2 and 0 is the next input and if it is B, what will happen? This is going to, if 0 on black blue and 0 on blue, that means current state is 0 on blue, that means remove blue plate. That means staying in the same state and we are going to remove this blue plate and after removing that epsilon, Q2 epsilon. And delta of Q2 1 green, 1 and green, Q2 1 and green, that means remove green plate. That means again it is staying in the same state, Q2 epsilon. Okay, now red and Q2. If you have red and Q2 without waiting for the input, remove red plate. That means here you have a delta of Q2 0 R and delta of Q2 1 R. What will happen? For these two cases, you are going to remove the red plate. That means if such a thing happens, what will happen? You are going to, that means without waiting, that means without waiting for the input, remove red plate. That means stay in the same state and red plate is also removed. That is why you have emptied the stack. In this way you have emptied the stack, and this is the way you are going to process WCW raised to R. So this is an example of a deterministic PDA. That means every move is deterministic. And now we are going to discuss. So processing this WCW raised to R is very simple, because if you have, say, these are the transitions, and I will show you how this is working. This is working. Suppose that you have an input, say 0 0 1 0 1 0 1. That means here you have in between C, and suppose that 1 0 1. Suppose that this is the symbol. That means this is W. Suppose that you have 0 0 1 0 1 and 1 0 1 0. Suppose that this is a string, and this is W and this is W raised to R. That means 0 1 0 1 1 0 1 0 1 0 1 0 is written here. That means this is WCW raised to R. Now what I am going to do is, suppose that the next input is 0, and so the stack is symbolically represented by this. Here you have the stack. This is the stack, and bottom of the stack is having red. Once you have 0, what will happen? You are going to push blue, and once 0, what will happen? You have pushed green. For this 0, you again pushed blue. For this one, you have pushed G, green. After this C, that means up to this point you are in state Q1, and once you read this C, you have switched your state to Q2, and in Q2, if the top of the stack is having green and if your input symbol is 1, Q2 1G, that means you have popped this green, and for this 0 and B, you are going to pop this. And for this 1 and green, again you are popping this, and for Q2 0 and blank, again this is pop, you have popped this. That means you have reached the end of the stack, and upon reaching this Q2 R, then you have, we are going to pop this also. That means now the stack is empty, and once the stack is empty, you can easily accept that string. That means this is acceptance by final state. It is acceptance by empty stack. That means emptying the stack.